Okay, so picking up where we left off last time, just a quick reminder, we were talking about this idea of flux through a curve, which is morally equivalent to the idea of flux through a surface. It's just a two-dimensional fluid moving through a one-dimensional, line, right, curve, as opposed to a three-dimensional fluid flowing through a two-dimensional surface, right? So totally analogous, one dimension down in some sense. And what we argued last time was because of some clever little geometry arguments that we could make, we could take the integral that would represent adding that up over an entire boundary curve. We could rewrite that as a good old-fashioned regular vector line integral, for which we have many tools, such as Green's theorem, and then, a couple of details to keep track of, and we've got ourselves a new theorem that you can compute outward-oriented boundary flux with an integral on the interior, specifically an integral of divergence. Okay, so the point of view, just to say it even more briefly here, is that where that ultimately came from, aside from some little clever geometry arguments, the heavy lifting was done by Green's theorem, right? Green's theorem was the thing that allowed us to turn, stuff happening on the boundary curve to stuff happening in the interior, right? So this, again, was doing all the real work of this result. So a lot of people will call this a version of Green's theorem, which is great. So I'm going to make the observation now, just picking up from there where we left off, that in fact we don't have to piggyback on Green's theorem at all. Boundary flux, forget about circulation temporarily, right? Boundary flux by itself is an accumulating quantity. Right? And so we forget about Green's theorem, forget about circulation, and forget about previous arguments we've made about accumulation. If we have a new accumulating quantity that accumulates over areas, we could go through the same kind of an argument and talk about, well, it accumulates, and therefore it is a kind of a stuff that we can view as distributed over the interior, and therefore it has a corresponding density, and the whole of some of the parts, you write it all down, and you end up with your own independently derived new accumulation theorem. And of course, it's exactly what we've already derived. So I want to take stock here now as we go through, and we're going to add to this collection as time goes on, the various different accumulation theorems that we have so far. Right, now the first one is the super obvious, and we did this a long time ago. This is just an observation that, the mass, the whole is the sum of the parts. Well, of course it is, right? And there's this idea of density, meaning that I can, I can do like this. I can talk about how a little piece of mass relates to the size that it's contained in by way of this thing called density. And boom, I've got a quantity, an accumulating quantity, computed as a double integral. Yawn, right? This is what we made integrals for in the first place, right? So that's not the surprise. The surprise is how these other theorems that are not about physical quantities at all, but are about geometric, you might say, algebraic, you might say, abstract quantities that behave in exactly the same way. And so as we, totally analogous to this mass idea, circulation has this same feature, that the whole is the sum of the parts. Outward-oriented boundary flux, as we just noted. The whole is the sum of the parts. Likewise, for each of these, just like with mass, you can talk about how much stuff relates to how much size by way of corresponding notions of density. And so for the same reason that we call this mass density, likewise, this we're going to call circulation density, this we're going to call flux density. We hadn't said that last phrase as of last time. So, but notice the pattern. This is an integrand. It relates stuff to size, thus density, and mass density specifically because mass is the relevant accumulating quantity. Well, likewise, Green's operator, circulation density, as previously noted. Circulation because circulation is the accumulating quantity. And now divergence we're going to call flux density. Just extending the analogy, right? It is a density. It is literally telling us stuff, in this case, this accumulating quantity called boundary flux, per unit size, still area. So weirdly, very weird, and certainly nothing we could have anticipated back in Chapter 3 when we first saw divergence, right? But what we see here is that it is literally telling us a density of an accumulating quantity called boundary flux. Okay, so I think I'm a tremendous fan of this sort of observation about the extremely strong relationship between these different theorems. And this, I hope, will motivate trying to think of these theorems kind of in the same way that we think of this, unremarkable, this is not at all disturbing up here, what we're talking about mass, right? Use this as a model for how to think about these two theorems down here, because structurally they really are kind of the same strategy, same observations, just about different quantities. Okay. All right, now I'm going to add to the list. Here's another accumulation theorem. Good news, this is one you've seen before. It's the fundamental theorem of calculus. Fundamental theorem of calculus, I claim, can, and in this course I think should be viewed as an accumulation theorem. Now, you may have previously thought of the fundamental theorem as a nice way to compute integrals, and it is, and I'm all for it, and that's great. Don't throw that away, but we're just going to kind of set that aside for the moment. And you can also view it in various other different ways. But I'm going to make the case here that this is a theorem about this quantity called change that I'm going to denote with a delta. So when I say change here, here's my formula, right? Just literally, if you give me an interval, then what I'm going to call the quantity of interest on that interval, it's not mass. I'm not interested in how much mass is in that interval. I'm not interested in any of various other options. The quantity is, how much does your given function f change over that interval? Then it's an accumulating quantity. Not a hard pitch. If you think about, just as an easy example, the amount that, let's say, my height changed from age 0 to 5, and then from age 5 to 10. Well, total, you add those up, and you get the amount that my height changed between ages 0 and 10. Right? Literally, the whole of the sum of the parts. Right? So, whole being the sum of the parts, I write down that. Right? And then, now, as I've done in these other theorems, let's look at this equation. And now just, why is this equation here true? Why is, change equal to derivative times input size? Oh, this is just dy is dy dx times dx. Right? Now, we normally think of that in some sort of geometric terms. Right? We think of it as the rise over the run. Oh, let's see here. Good color choices. Okay, that's good. Think of it as the rise over the run, and therefore the ratio, rise over the run, is the slope. So we think of f prime as being a slope typically. And yeah, sure, cool, right, I'm all for it. In this context, let's instead think of this as being not rise over run, but stuff, this accumulating quantity called change, stuff per unit size. This dx representing a size of a piece of the domain. So this is stuff per unit size, and stuff per unit size is a density. So again, now I know you all have multiple existing sort of points of view on how to think about the derivative. What is f prime? Again, it's a slope, it's a velocity Various other probably some. I like this idea. Somebody floated one time. A lot of people think of F prime as being a sensitivity. Right. So if you change the input, then the output's going to change, and how sensitive is the output to changes in the input? So there's various different ways to think of F prime. I'm going to add to that collection of points of view. Please now, at least for what we're doing here, try to think of derivatives as being a density. Okay. All right. So yet another density theorem, that accumulation theorem, whatever you want to call it. Just like the three that we noted on the previous page. So what I like about this observation, I'm a big proponent of the idea of analogies and using analogies to help you understand things. One of the big advantages of thinking of the fundamental theorem in this way, I'm going to try to get all this on the screen at the same time. There, that's good enough. So let's think about this suggestion that I made a while ago, that you should think of, you know what, let me actually scroll back to where we did this. Almost there. Yeah. So I made this somewhat unsatisfying, hard to swallow, big ask of, yeah, I know we compute the circulation on the interior, on the boundary. Of course, that's where we compute it. It is literally boundary circulation, but I tried to try to think of that as something that's actually happening in the interior. It's in the interior, and we just happen to measure it on the boundary, but it's actually in the interior. And I know that's a tough buy, right? I mean, it doesn't feel like it does at all. So with that in mind, let's come back to the fundamental theorem point of view here. And I'm going to make the exact same observation here. Not about circulation, but now about this other analogous, different but analogous accumulating quantity change. I'm going to claim that while we measure change by looking at these values, specifically I'm going to look at the value of the function at A and B, right? These points here, A and B, that's where we measure change. You want to write down the formula for change? It's f of B minus f of A. Right? It's that right there. And now I'm going to make what I think a much more easier assertion to buy. Modest observation that, yeah, we measure it on the boundary, but that's not where it happens. Right? Where does this function change? Is the change happening at these 2 points here? No, nonsense. It's perfectly obvious. You can look right at this picture. It just leaps off the page. You can see where the function is changing. That's the process of the function. That's not very visible, is it? Let me pick a different color. That is the process of the function changing. That happens at these points. That's where the change is actually happening. It's in the interior. Right? So now again, I think this is very believable. Well, of course change happens in the interior. I can see it happening at these values of x. Right? And the boundary is just kind of how we measure it. So with that in mind, and keeping in mind, this is another accumulation theorem. Right? Just like Green's theorem is an accumulation theorem. I hope that'll make this suggestion go down a little easier. That, yeah, computation happens on the boundary, but I'm asking you to interpret it as being a thing that accumulates over the interior. So again, it's just an analogy. I hope this might help you digest, again, this interior accumulation point of view. One last observation I'll make is that not only does this help, I hope, suspect and hope, does this help us digest the idea of stuff happening on the interior, but the derivative itself, the integrand itself, tells us specifically where and how much. Right? So if I were to draw the derivative here, well, the derivative would be 0 until I get to about here, at which point it would come up and kind of level off about like there, and then it'd be 0 again. Right? This is where this is what the derivative would look like. And notice, by virtue of where it's non-zero and how large it is, it's, again, literally telling you where the change is actually happening. Right? Does that make sense? Okay. So this also, this also is a pattern that continues through all of our various accumulation theorems that we're going to see in this class. We've already seen a couple of them. The integrand is a density, and it tells you where and how much in the interior your accumulating quantity is happening. So again, step one, digest that statement in the context of the fundamental theorem, where you can see the whole graph and it's pretty familiar concepts, and this is all just a lot easier to kind of buy. But with that in mind, and now here's a silly example. There we go. Silly, obvious example. If I were to look at this function f of x equals x squared, whose graph I have a picture of right there, and if I were to ask this silly question, okay, where's that change happening? The function changes over this interval from 0 to 3. The total change is 9. But where is that actually happening? Well, again, the integrand, f prime, easily computed. That's the thing that tells us how much the function is changing at different places. And so to the sort of obvious question, where is this function changing more? Is it changing more at 1? Is it changing more at 2? I just look at these values of the density and ask, where is the density biggest? Wherever the density is biggest, that's where more of that stuff is. Right? So where is the density the biggest? Well, here at x equals 2. That's where there's more change happening. And again, we get visual confirmation. Looking at the graph here, you can just perfectly obvious see that, yeah, it's changing more here than it is there. So by analogy, and here's where I'm going to ask you to sort of extend the analogy, whatever intuition you have from the fundamental theorem that we were just discussing. The same thing happens with Green's operator. Green's operator tells you where and how much the circulation is happening. Okay, so let me walk you through that. If you look at this vector field and this curve that I have here, claim that there is a positive circulation there, and this is a good little exercise to kind of think through. Okay, wait a minute, how do you measure circulation? Circulation, you're just measuring line integral. I can kind of see as I look along in here that I'm getting negative line integral along in here because the curve is going that way, the flow is going this other way. So to what extent is the fluid flowing in the direction the curve is going? Well, negative, because it's going the wrong way. By contrast, over here, we get positive circulation. Here the flow is in the direction the curve is going. But check it out, way longer, way stronger current, you might say, over here. Right? The field vectors are bigger vectors here. So there's a small amount of negative line integral up here. There's a large amount of positive line integral down here. So small negative, large positive, adds up to positive. So again, there's a positive circulation here. Where is that positive circulation happening? Well, it's definitely not happening here, right? Imagine, now just use geometric intuition. We're not getting, notice no algebra in this example here, right? So let's just think geometrically. Here's my little leaf I drop in the creek. I see how the water is flowing, and notice the water is flowing in such a way that it's kind of hitting the leaf kind of the same on both sides, and this leaf is pretty much just going to go downstream, just kind of straight. There's no rotating, there's no spinning happening. And likewise, down here, again, it's a faster current. The leaf is going to go downstream faster, sure. But again, it's being kind of pushed sort of equally on both sides. There's the fluid is not rotating here. Right? And this will be reflected in the value of Green's operator. If you compute Green's operator of the vector field here, at this point here, Green's operator will be 0, and likewise there, Green's operator is 0. But if you were to look at a leaf that you drop right here, let's see, I'll do it right here like that. Now again, let's just think geometrically, physically that is, I guess. Well, this leaf is going to go downstream. It's going to follow the flow line, of course, right? But it's only being pushed a little bit on the left, from the point of view of the direction it's going. But it's being pushed harder on the right. So here's what I think is going to happen. My physical intuition is being kind of spun counterclockwise, predominantly by the fact that most of the flow, most of the strong current anyway, is down on the bottom side, pushing it to the right on the bottom side, meaning it's gonna kind of do that as it goes downstream, right? It's going to be sort of rotating counterclockwise. And Green's operator will be positive. Here, Green's operator will be positive. So again, the density, this time we're talking circulation as our accumulating quantity. So circulation density, Green's operator is the density in question. And it's positive in here where the circulation is actually happening. We measure a positive circulation around this boundary. That circulation is coming from the interior. It's not coming from here. There's no rotation happening here. There's no rotation happening way up here. The rotation is happening in the middle where there's literally leaves twisting as they go. Right? And that's where the circulation that we measure on the boundary is actually coming from. Is that cool? Everybody happy? Likewise with flux, same sort of deal. I'm going to move a little bit more quickly through this one. If I look at this, whoopsie, I just messed up. Let me do that again. If I look at this curve, and now this curve, of course, again, is a boundary. Boundaries are oriented outward. That's our convention. Right? Let's think about how much outward-oriented boundary flux we have here. Well, our vector field is, we're going to get a little bit of negative outward-oriented boundary flux here because, again, outward means positive. This is inward, so, small amount on this left edge. But then, check it out, a very positive, highly, much greater magnitude of positive outward-oriented boundary flux over here. Longer field line, longer field vectors. Right? So there is a positive amount of boundary flux. Where's that happening? Where's that flux coming from? Well, it's not coming from it's not coming from here. If you look in this general area, there's just as much water flowing in as there is flowing out. The field lines are just as strong entering this area as they are leaving this area. So there's no boundary flux happening here. And again, you can compute divergence. And at this point, the divergence of the vector field would be 0. And likewise over here, the divergence of the vector field there as well would be 0. Where the divergence is coming from, the stuff that I measure on the boundary, where it's coming from, color choices, is this gray area in here. And you can see there's a relatively small amount of flux going in. There's a larger amount of flux going out. This is where you would measure a positive divergence. So again, divergence, the density is telling you where the stuff is happening that you're measuring on the boundary. How we doing? Is everybody on board? Yeah.
I'm sorry, I don't understand why it would be positive there.
Yeah, well, right. So you got to keep in mind what divergence is and different ways to think about it. But the point of view, let's see here. Yeah, sure. The point of view I'm taking here, right, is that divergence is flux density. So I'm looking at, on each little piece, I'm looking at, okay, how much flux is there happening on that boundary, and then divide by area. Right, so flux per unit size. And so if we look at our scenario here, let's look at this picture right here. How much flux is happening? If I were to look at the boundary curve here, right, how much flux, how much outward-oriented boundary flux would I have? Well, there'd be a little bit of negative on the left side because it's not outward, it's inward, but with relatively small vectors. On the right side, there's positive because it's outward as it should be, but with relatively large vectors. And so there's going to be a small amount of negative, but then a large amount of positive, and those add up to positive. Does that make sense? There's a lot to digest, right? A lot of sort of connections to make in your mind. I'm pointing out that several phenomena, several theorems are all kind of doing the same thing, right? Fundamental theorem of calculus, kind of like the 2D divergence theorem, kind of like how mass accumulates. I know it's a lot of dots to connect, right? So give yourself the time as necessary to digest these ideas, but ultimately there's just fantastic intuition to be had. If you want to feel like you have a good sense for, why does the divergence theorem work? Why does Green's theorem work? And how do I think about it intuitively? These are the ideas that do that. And it's a lot. And give yourself the time as needed to choke this all down. Okay. All right. Just as an algebraic example, now coming back real quick, we talked about this example, and I proposed this as being a silly example because I can just look at the picture. I don't need any algebraic help on this one particularly. Of course, it's perfectly obvious. The function's changing more at 2 than at 1 because, look at it. But I also know how that algebra breaks down, right? The algebra telling me how much things are changing. Derivative. Again, old news. Y'all have known this since Calc 1. And that resolves it for you algebraically, even though the geometry was clear. Well, thinking about these other accumulating quantities, the geometry just isn't going to be very clear, frankly. Looking at some weird vector field where the field vectors are kind of every which way, it's really hard to break it down. It's not like the simple examples that we just looked at. So we won't have geometric or physical, in most cases, sort of, freebie points of view. But the algebra is still there. So given this wacky vector field here, I wanted to be in the highlighter mode here. Given this wacky vector field, this vector field F, there's a certain amount of circulation around the boundary of whatever we're looking at. There's a certain amount of outward-oriented boundary flux through the boundary of whatever we're looking at. How much of that's happening where? Is there more boundary flux? I got ahead of myself. Is there more circulation happening at this point or that point? And again, you can't tell geometrically from the picture, but what you can do is remind yourself that circulation is detected by circulation density, which is easy to compute. And you can just plug in the 2 points. Plug in your 2 points, right? And just see, where's the circulation density greater? And the circulation density is greater at this point, 2, 4. So that's where there's more circulation happening. And likewise, if you want to know where there's more flux happening, you look at flux density, aka divergence. plug in your 2 points. See where it's bigger. Wherever it's bigger, yeah, that's where there's more flux coming from. Yeah.
Can you briefly run through how you got those equations for Green's theorem and
Oh,
flux?
yeah. So, now the equations are how I computed these results right here.
How you got the equations?
Oh, yeah. So that's I never really did talk about that, and that's computations that we're not gonna do in this course. But so the formula that I use here to compute Green's operator is, let me just scroll back to it here. Almost there. Any second now. Yeah. So that was this conversation here, and I just asserted that this is the formula that computes Green's operator, aka circulation density. There is a calculation. It's in the book. You can read it if you want. To me, it's a bunch of details. Conceptually, I don't think those details are key. They're of course key for the purpose of rigor and making sure that that the algebra works out. Yeah, of course. But for what we're doing here, just trying to get an intuition for what these things look like and how they behave, far more important to know that you should interpret this formula as circulation density than it is to know the algebra of where this formula came from. My opinion, of course. Okay. So, moving along. 6.3. We're going to talk about yet another accumulation theorem. I've kind of lost count now. Let's see. We have the mass was kind of our first, mass and, etc. Other physical examples were our first accumulations. I don't even want to call it a theorem. That was just what integrals were for in the first place. But then we had Green's theorem and the other version of Green's theorem, and then the fundamental theorem of calculus. We saw is actually technically kind of the same thing. So we're up to 4. We're about to see now our 5th example of an accumulation. Okay, it's called the fundamental theorem of line integrals. Here it is. You can probably notice right off the bat that this, just the way it lays on the page looks just like the fundamental theorem of calculus, doesn't it? It just smacks of the fundamental theorem of calculus. Integral is f of b minus f of a, for crying out loud. It looks exactly the same. So that's why we I think that's a good motivation for using kind of the same grammatical construction here in the name of this theorem. But the theorem itself, you'll notice, is about specifically a line integral. This is not a Calc 1 integral. Line integrals are a different critter. Right? So thus the name, fundamental theorem of line integrals. What's going on here? Why does this theorem work? Well, again, it's about an accumulating quantity. Again, our accumulating quantity is called change, just like with the fundamental theorem of calculus. The whole is the sum of the parts. And again, well, of course it is. So let's walk through an example just for intuition purposes. Here's the algebra, if you like the algebra. But let's think about this just intuitively. I like to think of this as being like a mountain road. Right, this being the curve over which we're going to be doing a line integral, and let's think of it as what I'm actually interested in measuring along this road. Let's suppose I'm interested in my altitude, and how much is my altitude changing? Right? So again, change, altitude change, but change is what we're going to be interested in. So, okay, well, now modest observation, if I keep track of how much my altitude changes over the first half, and then if I think further, how much does my altitude change over the second half, you add those up, and that'll tell you how much your altitude changed over the whole drive. Well, of course. Right? If you gain 3,000 feet elevation over the first 10 miles and another 4,000 feet elevation over the next 50 miles, well, 3,000 plus 4,000, you've gained a total of 7,000 feet. Again, it's no surprise there. Okay, well, when you have an accumulating quantity, there is an associated density. And I'm going to revive an old formula from long ago, chapter 2. If you have some function and you want to know how much the output changes given how much the input changes, and keeping in mind that our input change is the displacement, right? When you're moving in the plane, your displacement is the dx vector. Well, output change and input change relate by dot product with the gradient. So reviving that old formula, again, chapter 2, and recalling that dx is TDS. Right? Important little rewrite. Again, flashing back to long ago. Notice now our formula can be interpreted in terms of density. Here's our formula, and check it out. We've got accumulating quantity of stuff per unit size. ds, right? Length representing size of a piece of curve. And so the density here, what we're going to call change density in this case is this little formula, gradient dot T. And with that noted, I'm going to come back in a minute to this stuff. Ignore this for the moment. But for the moment, looking at this purple formula, and we have stuff per unit size right here. Notice all I'm really doing is plugging in the established formula we just discussed for change density. And again, I have this accumulation result. Change accumulates the sum of the parts. And on any little piece, quantity per unit size is density. Is that cool? All right. So now before we go on to the other version here, I'll point out that this is a new theorem. See color choices. Here we go. Right here. In fact, this is pretty much our theorem that we saw above. This is our fundamental theorem of line integrals. This is a vector line integral, written in a weird way, to be fair. But vector line integral, and it's literally computed by f of v minus f of n. How we doing? Yeah.
So T there is a transformation matrix.
One more time, I'm sorry.
So T there is basically just a transformation matrix.
T?
Yeah.
This is our unit tangent vector.
The tangent.
Yeah. So I'm making a flashback to, there was a bunch of geometry that we wrote down back in chapter 3 concerning the participants and objects relevant to as you move along a curve. And this capital T is the unit tangent vector. Yeah. And so you can look back at all the related formulas there. Yeah. Okay, so now, what's the deal with all this other business? What's the deal with this bottom formula here? And it's actually not that big of a deal. I'll remind you, this is, again, actually old news. dx is TDS. So we established that several chapters back, right? And so that gives me my rewrite, and so I can reconceive more conveniently, you might say, of the fundamental theorem of line integrals with this integral here on the right. Right? But this kind of messes up our density point of view a little bit, right? I mean, when you're looking at the original version, you can easily make the case that we're talking about stuff being stuff per unit size times size, and that's satisfying. So what's the analogous interpretation of this formula here if I want to think of stuff as, how am I supposed to interpret the gradient by itself? How am I supposed to interpret dx? Which, look, the magnitude of dx is my ds, but this is a vector. It's got a direction. How do you make sense out of something that tells you not only a size, but also a direction, too? Okay, well, this is just a take. I think this is very handy, though. I'm going to encourage that we think of dx as being, I'm going to call oriented size. Because, again, think about what dx is. This is a direction and a magnitude. The magnitude is the size. So what dx has that ds doesn't is a direction, namely an orientation. It's telling you which way that ds is pointing. Right? So I think oriented size is a pretty reasonable take on that. And with that in mind, the gradient by itself, then, I like to call that oriented density. And again, this is this is something I'm just asking you to kind of be flexible about in terms of interpretation, right? This thing I'm calling oriented density, I'm calling it oriented density because it relates to oriented size, and stuff is density times size, sure, but stuff could also be thought of as oriented density times oriented size. So it's just kind of like I say, a different way of kind of thinking about morally the same thing. So this point of view, this idea of thinking of the gradient vector as being an oriented density, we're going to use that later on. This is a segue to a more sophisticated idea that we're going to talk about later in Chapter 7. One of the last things we'll do in Chapter 7 is talk about something called Stokes' curl theorem. And we're going to find ourselves faced with this pretty challenging question of what am I supposed to make of this thing called curl? And it's going to be really analogous to this. It's going to be an oriented density of a sort. All the details are different, of course. But so I'm planting this thought early, this idea of an oriented density, kind of an interpretation of how to think about a vector as a density. Planting that thought now, we'll make use of it later. Okay, so let's do one. Let's compute. And by the way, coming back up here to our theorem, I think there's good intuition to be had for thinking of this theorem as, in terms of accumulations. But in terms of how are we going to use this day in and day out, what does this help me actually do? Oh yeah, this helps me compute integrals. You want to compute an integral? Bam, right? Pretty convenient little formula for how to do this. All I need, right, if you find yourself looking at an integral and you don't know how to compute it and you don't want to do it the old-fashioned way, oh, yeah. Well, all you need to compute that, you just need this function here called little f. You just need to know a function there, little f, whose gradient is your vector field integrand for the line integral you're trying to compute. And if you can find that function whose gradient is your integrand for your line integral, off you go. Bada bing, bada boom. Okay, so let's do one. Here's a line integral to compute right here. Vector field given, curve given already pre-parametrized. Right? And the question is compute a line integral. Now let's talk strategy for just 1 second here. Y'all are going to be encountering questions on exams and homework and in your futures, right outside of this class. Vector line integrals will naturally arise in various different ways, and they will not announce themselves as do this one with this tool, right? So you have to decide for yourself which tool you're going to use. Again, we've got various different tools that apply in various different circumstances of how to compute these things. There is a temptation here from how the question is written to parameterize and plug and chug. And the temptation is based on the fact that it's already parameterized. Like it's almost kind of begging for you to take this parameterization and plug it in there and take a deep breath and plow forward and compute the answer. And you could do it, but I don't think you want to. You think about how would that actually play out. Keep in mind when you're doing a pullback, right? The thing that is your first coordinate of your parameterization, that is literally x, and so that would go here and here. And then the thing that is your second coordinate, that is your y, and so that goes here and there. And so your integral is going to be a nasty trig integral. It's going to have a bunch of trig in it all over the place. And again, not that it can't be done. Sure, it could, right? But some of those get a little inconvenient. Okay. So here's the much better. Don't just follow your initial temptation and say, "Wow, parameterization. I guess I'll pull back through the parameterization." Notice, and we'll talk more later about how to notice this kind of thing. Notice that my vector field here is a gradient. I mean, just easy arithmetic to do, right? You can take this thing right here. This is going to be my little f. You can take that thing right there. There's my little f. Take its gradient. Easy little partial derivative. Easy partial derivatives. And yep, sure enough, my vector field is a gradient of that thing right there. And it's all over but the shouting. Now, I have my little f function. And fundamental theorem of line integrals tells me that my line integral then can be computed as just f of b minus f of a. Now, the one little bit of trouble that I have to go to, I suppose I do have to figure out where does this curve start, where does this curve end. And so, yeah, I've got to take my starting value of t and plug it in and see what my starting point is. And yeah, I've got to take my ending value of t and plug it into the parameterization and see where my ending point is. Find your a, find your b to be able to compute f of b minus f of a. But that's easy arithmetic, right? Let's see here. A goes there. B goes there, and plug and chug and 0 and done. I didn't have to do any trig integrals. I didn't really have to do any integrals at all. We just have an answer that just pops out of the theorem very conveniently. That makes sense to everybody? Okay, let's see here. We are basically out of time, so I'm going to go ahead and stop early, uncharacteristically, and we'll pick up here on Wednesday. So, yeah, see y'all later. Have a good one.